Okay, the purpose of this presentation is going to be a little bit different. There's a lot of different topics that people talk about, and there's specific technical jargon. Instead of just speaking general English, which isn't specific enough, precise enough for technical topics, there's one sort of jargon for the economists use, one sort of jargon that mathematicians use, one that chemists use, physicists, etc. They have their own glossaries and so on. So, as an example, I'm going to be comparing two topics that are seemingly different, but it's really the same topic. The reason it sounds so different is I'm going to be doing it both in English, of course, but one is the language of chemistry, and one I'm going to do in the language of mathematics. And then I'm going to be drawing pictures to show you how we're really talking about the same thing. In fact, what it really is that mathematics is the more general version, and chemistry is a specific application of this mathematical topic. So this is how you would say it in chemistry. If you've taken general chemistry, or especially organic chemistry, this might sound familiar. I'm going to be talking about enumeration of constitutional isomers of aliphatic alkanes. Now, if you have no idea what that means yet, don't worry, I will be showing you. Chemistry is not a prerequisite to this. Likewise, a mathematician, what he would probably say is that you're going to be counting nonisomorphic trees with unlabeled vertices and a maximum vertex degree of 4. Now again, if you have no idea what that means, because this is actually from tree theory, which is part of graph theory, which is from discrete math, which is pretty high level math, then that's okay. I'm going to be drawing pictures so you can follow along anyway, and hopefully you'll find it interesting comparing how there's really two very, very different ways to say the exact same thing. Okay, so let's get started by defining a few of these big words that we're going to do. So a chemist, he would define an isomer as compounds that have the same molecular formula but different structures. For example, here are two compounds that have the exact same formula, C4H10. Now if you haven't had organic chemistry, oops, I think I made that too big, haha. Okay, so anyway, so if you haven't had organic chemistry, you probably don't realize each of these corners or endpoints is a carbon atom, and then you've got enough hydrogen to surround it. So you've got 3 hydrogen here, 2 hydrogen here, 2 hydrogen here, 3 hydrogen here. So this is normal chain butane, or just N-butane, or just butane for short. This compound here has got the exact same formula, C4H10, but you'll notice you still got the 1, 2, 3, 4 carbon atoms, and you've got 3 hydrogen atoms, and then 1 hydrogen atom here in the middle. And this one's called isobutane, or 2-methylpropane. A mathematician would say isomorphs are graphs that can be related to each other by a bijection. Now, I'm not going to try to define every last word, but hopefully, here's 2 examples. These two graphs are isomorphs of each other. Notice you have 4 vertices, just like we had up here, but these two aren't the same as that. Notice each vertex is connected to the other 3. Same here. You have 4 vertices, and each one is connected to the other 3. So these two are isomorphisms of each other. Okay, so let's start with n equals 1. So if n equals 1, in chemistry, we get the formula C1H4. This is the formula for methane. This is what it looks like. You have a carbon atom surrounded by 8 hydrogen atoms. There's only one way to do this, so we say that methane has just one constitutional or structural isomer. Now, in mathematics, we define order as the number of vertices in a graph. Since we said n is equal to 1, we mean that the order is equal to 1. So here's our vertex. That's the entire tree. There's only one way to draw a dot. Therefore, we say there's just one non-isomorphic tree. And this is what methane looks like in chemistry. You've got the black carbon atom surrounded by the 4 hydrogen atoms. Now for n equals 2, we have a similar situation. In chemistry, that'll give us C2H6. So this is what it looks like. We have 2 carbon atoms, each of which has 3 hydrogens on it. The name of this molecule is methane. Notice each one of these carbon atoms connects to one other carbon atom. So we say that this is a primary carbon, or a 1-degree carbon. And there's only one way to do this, so we say that ethane has only one isomer. Now in mathematics, we'd say that our graph has order 2. Here we are. We have the first vertex here, the second vertex here. Notice they are connected. They have to be connected. Now if you had 2 dots separately, that would be a perfectly good graph, but it wouldn't be a tree. A tree is a connected, acyclic, which means no circles, I'll show you that later, simple graph. Simple means only one connection between the two. There are perfectly legitimate graphs where you have 2 or 3 or 10 connections between vertices, but that's not a tree. That's a different kind of graph. So again, there's only one way to do this, so we say that for order 2, there is only one non-isomorphic tree. So continuing on, what if n is equal to 3? Well, in chemistry, we get the formula C3H8. Oops, I forgot to write the name. This is propane. Okay, so as you can see, we have 3 carbons in a row. And off the 2 end carbons, we have 3 hydrogens. Off the middle carbon, we have 2 hydrogens. Now the 2 end carbons, they each connect to one other carbon. So we say this is a primary carbon, this is a primary carbon. This carbon here in the middle, it connects to 2 other carbons. So we say that's a secondary carbon. Now notice there's only one way to do this. Here's the molecule we're talking about. This is a propane molecule. And you can rotate it around all you want. And, well, at room temperature, this I think would happen anyway. And there's only one way to do this. So there's only one isomer of propane. Now in mathematics, we have a graph of order equals 3. Now I drew this 3 different ways to prove a point here. Here we have the 3 dots in a row horizontally, and notice you still got the exact same thing up here. You got 2 ends and then in the middle. I drew it crooked like this or vertically like this. Any of these are perfectly valid, and they're the exact same thing. Either way, you have the 2 end vertices or nodes, and then you have the middle vertex or node. So these 3 are isomorphic. So these only count as 1. There's only one non-isomorphic tree for order equals 3. Alright, so let's talk about chemistry, or for n equals 4. For n equals 4, in chemistry the formula is CnH, 2n plus 2. We get C4H10, which is butane. Now there are 2 forms of butane. One, we can have all 4 carbons in a row. That's this one right here. Notice the 2 end carbons, they each have 3 hydrogens. 3 hydrogens, that's here. And then in the middle, each of the carbons has 2 hydrogens. That's this and this here. The other constitutional isomer, or structural isomer, is this one right here. Notice you have 3 in a row, and then you put the 4th carbon off the middle carbon here. So you've got all 3 of these end carbons with 3 hydrogens, and then this middle carbon with just 1 hydrogen. So here we have a CH3, 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 and then just 1 hydrogen here. Now you'll notice then, this isomer here, that you have 2 end carbons that are primary carbon. Primary carbon means it's next to 1 carbon. And then you'll notice you have 2 of these carbons here that are secondary carbon. Secondary carbon means it's next to 2 carbons. Secondary carbon means it's next to 2 carbons. Now over here, you have 3 carbons that you might say are end. These are primary carbons because they're only next to 1 carbon. And then you have this carbon here that's next to 3 other carbons. So we call this carbon a tertiary carbon. Tertiary means 3 degree. So this tells us there are 2 structural isomers of butane. Now in mathematics, we say we have the tree and its order is 4. Remember, the order means we have the number of vertices. So we have 1, 2, 3, 4 points in a row, just like this, or vertices. We have the 4 vertices. Remember, the angle's arbitrary. We could draw this any angle we want, as long as they're connected like this. And that corresponds to this one up here. So now you can start to see how we're talking about the same thing in math and chemistry language. And then over here, we have the 3 in a row, and then the 4th one coming off the middle one. So this corresponds to that one up here. So again, we have these 2 nodes in here that are secondary, and then we have these two over here that are primary. So we have the degree sequence 2, 2, 1, 1. And then here we have this one node here that's tertiary, and then we have these three nodes that are primary. So we have the degree sequence 3, 1, 1, 1. So we have two non-isomorphic trees of order of 4. Now, continuing on the idea of n equals 4, there's one thing to point out. A chemist would say, as we're not worried about isotopes. Chemically speaking, different isotopes of the same element are all the same. So like carbon 12, carbon 13, carbon 14, we're going to just pretend they're all carbon. Therefore, carbon atoms are all the same. Now, mathematics, they're sometimes not as picky. For example, look at the way I've drawn these. This is the same n equals 4 that we had on the previous slide, but I've numbered the vertices different ways. Like here I've counted 1, 2, 3, 4, and I've switched them around in all these different orders. Same thing, here's the other non-isomorphic tree, and notice this one has 1 in the middle position, this one has 2 in the middle position, this one has 3 in the middle position, this has 4 in the middle position. So, if you were to label and somehow keep track of each separate node, then for n equals 4, you actually have 16 different trees. On the other hand, that's not what we're doing though. We're saying that all these vertices are the same. So these 4 trees are really the same tree, and these 12 trees are really the same tree. So they're really only 2 different unlabeled trees. Okay, so continuing on, what if n is equal to 5? Well, in chemistry, that gives us the formula C5H12, which we call pentane. Now, one way to do this, of course, would be just have all 5 carbon atoms in a row. The 2 end carbons each have 3 hydrogens, and the 3 middle carbons each have 2 hydrogens. We call this chain pentane, or just N-pentane. Now, another way would be to have 4 in the row, and then off either the second one, we put the 5th carbon. That way, we call this isopentane, or 2-methyl-butane. And then finally, the third way would be to have the 3 carbons in a row, and then off the middle carbon, we put both of these carbons. And this one we call neopentane, or 2,2-dimethyl propane. Yeah, propane. So, as you can see, this is 3 different ways. So there's 3 constitutional isomers of pentane. The important thing to remember, these 2 carbons, we have 2 carbons that are primary, 3 that are secondary. Here we have 3 carbons that are primary, 1 that's secondary, 1 that's tertiary. And then up here we have 1, 2, 3, 4 carbons that are primary. This middle carbon is surrounded by 4 other carbons. We call this quaternary, which means a 4-degree carbon, which means the carbon is next to 4 other carbons. Continuing on n equals 5, so we show that there are 3 constitutional isomers of pentane. We have the one with all 5 in a row, we call this N-pentane here. We have the one with 4 in a row, and then one side chain, we call this isopentane, or a 2-methyl-butane. And then we have the one where we have 3 in a row and 2 methyl groups off the middle one. So this one we call neopentane, or 2,2-dimethylpropane. So why does it matter? Well, hopefully you can see that these 3 molecules, they're different shape. And not really quite the same size either, even though they actually have the similar volume, but definitely different shape. So this translates into very different physical properties. For example, let's talk about the melting point in degrees Celsius. N-pentane melts at minus 129.8 degrees Celsius. Isopentane melts at minus 159.9 degrees Celsius. But neopentane melts at minus 16.6 degrees Celsius. Likewise, the boiling point, BP in degrees Celsius. N-pentane boils at 36. Isopentane boils at 27.7. And neopentane boils at 9.5. And the same with the density rho in grams per liter. N-pentane is 621 grams per liter. Isopentane is 616 grams per liter. And then neopentane is 586 grams per liter. So even though these three compounds have the exact same formula, they have different properties, all sorts of different physical properties. Now in mathematics, we can do the same thing. We can draw the 5, oops, forgot to write, so we're at order equals 5 here, obviously. A mathematician would say the order of the graph is equal to 5, because it's got 5 nodes. So you can have the 5 nodes in a row like this, and that gives us degree sequence 2, 2, 2, 1, 1. Or you can do 4 in a row and have 1 come off either middle one. So we get degree sequence 3, 2, 1, 1. Oh shoot, there should be a third 1 there. Haha. Okay. And then finally, we can do, like I said, the 3 off the row, 3 in a row, and then 2 coming off the middle here. So this is 4 degree, and then 1, 2, 3, 4. So we get the degree sequence 4, 1, 1, 1. Oops, forgot another 1 here. So, oops, oh, and I can't count, of course. All right, so that gives us 3 different non-isomorphic trees here for order equals 5. Now let's talk about what if we have n is equal to 6. Well, in chemistry that gives us the formula C6H14, which we call hexane. There are a couple of different ways to do this. Now you notice for big molecules we don't bother to show all the hydrogen atoms anymore because it's just understood for the type of molecule we're doing. You'll learn to do this in organic chemistry if you take organic chemistry. So here we just show this zigzag here, remember, because each carbon atom is just the bond angle. You draw it diagonally like that so you can tell what's going on. So it's just understood that each one of these corners here there's a carbon atom, and then at each endpoint there's a carbon atom, and then there's the hydrogen atoms to make up the difference. So here we have 1, 2, 3, 4, 5, 6 in a row. Here we have 1, 2, 3, 4, 5. Whoops, there should be too many. Oops. Okay, so there's 5 in a row, and then this one comes off the second one. Or here, we have 1, 2, 3, 4, 5 in a row, just like before, but then we have 1 coming off the third one. And then here, we have 1, 2, 3, 4 in a row, and we have 2 coming off 2 different places. And then here we have 1, 2, 3, 4, but we have 2 coming off the same place. So here we have a pair of primary carbons and a bunch of secondary carbons. Here we have 1, 2, 3 primary carbons, a couple of secondary carbon, and a tertiary carbon. Here we have 1, 2, 3 primary carbons, a couple of secondary carbons, and another tertiary carbon. Here we have 1, 2, 3, 4 primary carbons and a couple of tertiary carbons. And here we have 1, 2, 3, 4 primary carbons, a secondary carbon, and a quaternary carbon. Oops, so that gives us 5 constitutional isomers for hexane. Now mathematics would say the order of our graph is 6. So we can have the 6 in a row. Notice they don't care about angles so much in mathematics because in chemistry bond angle matters, but in math it doesn't matter. Just you could make a zigzag for all anybody cares. Or you could have 1, 2, 3, 4, 5 nodes in a row and have 1 come off the second one here. So now this correlates to this correlates to that one. And of course, rotating upside down is irrelevant. Or here we have 1, 2, 3, 4, 5 in a row, and then 1 coming off the third one, just like we did right here. And then here we have 1, 2, 3, and 4 in a row, and then we have 1 coming off the second, 1 coming off in the third. That's this one here. And then we have 1, 2, 3, 4 in a row, and we have 2 of them coming off this second one here, just like this one here. So here, we call this one just N-pentane. This one would be 2-methyl, no, this one is hexane. This would be 2-methylpentane. This would be 3-methylpentane. This would be 2,3-dimethylbutane. And then this would be 2,3-dimethylbutane. So here we get the degree sequence, what is it? 2, 2, 2, 2, 1, 1. Here we get the degree sequence 3, 2, 2, 1, 1, 1. Here we get the degree sequence 3, 2, 2, 1, 1, 1. Here we get the degree sequence 3, 3, 1, 1, 1, 1. And here we get the degree sequence 4, 1, 1. Oh no, wait, I forgot. 4, 2, 1, 1, 1, 1. Now, most importantly though, this one does not count. Now, the reason is, this is a perfectly valid graph, it's a perfectly valid tree. And of course, it does have 6 nodes. But remember, for our application, we're saying the maximum node degree is 4. This graph here, this center node, has degree of 5. So this is something we do not want to count for this application we're doing. So that's why we're going to skip this, it's irrelevant, and we have 5 different non-isomorphic trees of order equal n and maximum node degree of 4. Okay, continuing on, now what happens if n is equal to 7? Well, in chemistry we get the formula C7H16, which we call heptane, and of course there are a bunch of ways to do that. We can do all the carbons in a row, or we can do 6 of the carbons in a row and have 1 come off the second carbon, or we could have 6 in a row and have 1 come off the third carbon, or we could have 5 in a row and have 2 come off the second carbon, or we could have 5 in a row and have 1 come off the second carbon, 1 come off the third carbon, or we could have 5 in a row and have 1 come off the second carbon, 1 come off the fourth carbon, or we could have 5 in a row and have 2 come off the middle carbon, or we could have 5 in a row, have 1 come off the middle carbon, and then another 1 come off that one. Or we can have 4 in a row, 4 in a row, and then we could have 2 come off the second carbon and 1 come off the third. So that gives us non-constitutional isomers. All of these could be generically called heptane, but there's actually a way to name them. I'm not going to bother to name them all right now. Now in mathematics, we would say we have a graph of order 7 because we have 7 nodes. So we could have the 7 nodes in a row. That gives us degree sequence 2, 2, 2, 2, 2, 1, 1. Or we could have 6 in a row, 1 come off the second, which correlates to this. That gives us degree sequence 3, 2, 2, 2, 1, 1, 1. Or we could have 6 in a row and 1 coming off the third one, just like we did here. That'll give us degree sequence 3, 2, 2, 2, 1, 1, 1. Which, by the way, is the same degree sequence as this one right here. And then we could have 1, 2, 3, 4, 5 in a row and have 2 come off just like this. Or we could have 5 in a row, have 1 come off the second, 1 come off the third. Or we could have 5 in a row, have 1 come off the second, 1 come off the fourth. Or we could have 5 in a row, have 2 come off the middle. Or we could have 1, 2, 3, 4, 5, and then 1 come off that, and 1 come off that. Notice I drew an angle here just to fit it in. Remember what I said before, angle doesn't matter. I could have drawn it here or straight down or whatever, as long as the connections are correct. And then of course you could just do 4 in a row, and then you have 2 coming off this one, 1 come off this one. So a mathematician would say, for order equals 7, we have non-isomorphic trees, assuming unlabeled vertices and a maximum node degree of 4. Alright, so we've been talking about what happens if you have a certain n, how many do you have? In the case of chemistry, we'd say how many constitutional or structural isomers do you have? In the case of mathematics, we'd say how many non-isomorphic trees do you have? I'm going to show you the numbers here, just so you can see how they increase. For n equals 1, 2, or 3, we showed there's only 1. For n equals 4, we showed there are 2. For n equals 5, we showed there are 3. For n equals 6, we showed there are 5. For n equals 7, we showed there are 9. Now, I didn't bother to show it because my whiteboard's only so big, but for n equals 8, there are 18. For n equals 9, there are 35. For n equals 10, there are 75. For n equals 11, there are 159. For n equals 12, there are 355. For n equals 13, there are 802. For n equals 14, there are 1,858. For n equals 15, there are 4,348. For n equals 16, there are 10,359. For n equals 17, there are 24,894. For n equals 18, there are 60,523. For 19, there are 148,284. For n equals 20, there are 366,319. Now, I could have gone higher, but I think you get the idea. The bigger n gets, the number of non-isomorphic trees gets huge. Now, one thing I'd like to point out, though, if you were to actually make a molecule with the n equals 20, thanks to steric hindrances and other chemistry chemistry concepts, some of these would not apply. So the actual number of constitutional isomers could be a little bit less than this. But from a purely mathematical point of view, this is the official answer. Now, if you've taken organic chemistry where you had to learn to name these and so on, you're probably wondering, what is the formula to get from here to there? And that's why I became interested in this, because there isn't a formula. Alright, so continuing on the same pattern as before, if we have n number of carbon atoms, or vertices or nodes if you're thinking about graph theory, this is the number of non-isomorphic graphs. Again, this is the mathematical answer due to different chemistry concepts. Some of these might not be actual valid molecules. But as you can see, for like n equals 27, there are actually 240 million different constitutional isomers. Now, to calculate this, what they do is they actually just have these computer programs that go through and they actually draw every single, well, not draw it like on paper, but they compute every single possibility and they just make a huge list and then they count how many are in the list. There is no actual simple formula to find this number. And I'm going to show you why in a bit. Now, as far as the formula to calculate that, one thing that's close is something called Kaylees formula. Kaylees formula is really simple. You just take n to the n minus 2 power. Now, this will give you the wrong answer. This won't find what we're looking for. Because, one, it assumes labeled vertices. For our application, we have unlabeled vertices. Because, like I said, carbon atoms are all identical. Even if you were to use different isotopes, there's only so many isotopes with carbon you could use. Likewise, it assumes no maximum vertex degree. Again, carbon is tetrahedral. It's going to make 4 single bonds. Therefore, our maximum vertex degree is 4. And of course, this formula is a mathematical formula. Specifically for tree theory, it's ignorant of certain mathematical principles. For one thing, atoms are nodes or vertices. They take up space, namely the carbon atoms. Likewise, the bonds between carbon atoms and from a carbon atom to hydrogen atom, it's a certain length, it's a fixed length. And likewise, I didn't bother to write it down, but because the carbon atoms are tetrahedral, there's a certain angle between them. So because of that, they have to fit in a certain space. And not every single mathematical possibility is going to make sense in real 3D space. So you're probably wondering, as far as computing these numbers, how do you do a graph like this inside of a computer? Now, obviously they don't draw the hand and scan it with their flatbed scanner. What they do is they represent it with a type of matrix called a Laplacian matrix or an admittance matrix or a Kirchhoff matrix. So this basically is a matrix that represents the graph. Now, of course, just counting the number of possible graphs isn't the point. The point, it can also be used to find other properties of a graph. So here's how it is. Let's say for each point, oops, this should be a j. It's I comma j here. Okay, so if I equals j, in other words, the diagonal, you write the degree of that vertex. If I is, oops, this should be not equal to j. If I and j are next to each other, then you write minus 1. And if I is not equal to j and they're not next to each other, you just put 0. For example, here's a labeled graph. Now this is not a tree because it's got a circuit here. A circuit is a totally different type of graph from what we've been doing here. But anyway, and likewise, this one has labeled nodes just to make it easier to follow. So, for example, here's node 1. Node 1 is degree 2. So here at 1, 1, you have a 2. It's also next to point 5, vertex 5, and vertex 2. So at 1, 5, you have a minus 1. At 5, 1, yeah, this would be 5, 1, and 1, 5, you have a minus 1. And then at 1, 2, and 2, 1, you have a minus 1. And then everywhere else, for 1, you have zeros. Likewise, let's say number 4 here. So 4 is degree 3. So if you go to 4, 4 here, you've got a 3. It's next to 6, 5, and 3. So like at 4, 6, you have a minus 1, and at 4, 3, you have a minus 1, and then at 4, 5, you have a minus 1, and vice versa. And then everywhere else you have zeros. So this whole graph here is represented by this matrix. And this matrix, this is how they're able to do the computations with those various computer algorithms to calculate the number and so on. All right, I'm going to just wrap it up now. I kind of gotten off of my track of comparing chemistry to math terms because I've actually done this more in the math area than the chemistry area. So just to refresh, what were we trying to do? A chemist, he would conclude that there is no known formula to find the number of constitutional isomers of aliphatic alkanes. A mathematician, he would conclude that there is no known formula to enumerate the nonisomorphic spanning trees of order n, maximum node degree of 4, and unlabeled nodes. That is all.